So once again, welcome. We'll do the presentations for 20 minutes, a little about 5 or 7 minutes for questions and answers. Then we'll roll right into our next presentation. We have 10 presentations today, 6 this morning, starting at 9. And then we will start we have 4 more this afternoon, starting at 1 o'clock. Generally, we take questions only from our industry advisory board members. We welcome all the other guests to, by all means, listen and so forth. We welcome everybody here as well. I'd like to briefly introduce our industry advisory board members before we get going. Dr. Abadiah is our chair for the department. Good morning, sir. I'll go around my little room here with, with the tiles. John Palasic. Welcome, John, longtime member, former senior design coordinator. Dr. Atinaki on the faculty, Dr. O on the faculty, Dr. Shao on our faculty, Dr. Hu. Craig Shoemaker, I see Craig's name out there. Craig is on the IAB as well. Paul Pagano joining us for some of these. Paul's got his PPE on. Looks like he's in the field going between site visits or something, so that's awesome. Thanks for joining us. Dr. Liu is here, one of our newer faculty members. Good morning, Dr. Liu. Mary, thanks for joining us. Mary is our office assistant, strong supporter of our students, loves to be involved, and I'm looking to see if I missed anybody on our industry advisory board as I scroll down. If I missed you, speak up, please. I think I got everybody that's joining us this morning. Without further ado, Team 1, our first presentation, superstructure design for the 100th Street Bridge over US 131. Go ahead and share your slides and we can begin your presentation.
All right. Good morning, everyone. My name is Tom Rank, and our team consists of Levi Rowan, Dirk Smith, Arturo Lagrono. Our team is a large combination of experience in the construction industry, which combined with our engineering education gave us the necessary background to conduct the superstructure design for the 100th Street Bridge over US 131. The 100th Street Bridge over US 131 is located just south of Grand Rapids, Michigan, in Byron Center. The bridge had a long history of underclearance issues causing accidents as well as its service life was exceeded. In this design, while we primarily focused on pre-stressed concrete and steel girder design, we also conducted a variety of other work. Our scope of work for this project consisted of a schematic ramp intersection design, dual roundabout cost estimate, temporary traffic control plan, pre-stressed concrete and steel girder design, superstructure cost estimate, construction schedule, and an engineering design and construction summary. To acquire the number of lanes needed for the design of the bridge, a geometric intersection design was necessary. While working with our sponsor at MDOT, she recommended we use roundabouts on either side of the bridge as our intersection control type. Using a recent traffic study conducted by MDOT, we achieved both the 50 and 25-year traffic volumes. Once we acquire our traffic volumes, we use the 25-year to design the roundabouts as this is their typical service life. Using the future traffic data and a transportation software called Synchro 10, a model was constructed and simulations were ran. From the future data, AM peak hour traffic volumes for entering US 131 were used as they were the greatest. To produce a reasonable level of service for the intersections, right turn bypass lanes were used where applicable. While we designed these intersections for a 25-year life and achieved a level of service A, we also modeled the intersections for a 50-year bridge life and produced a level of service B. With acceptable level of service for both intersections for both 25 and 50-year traffic volumes, this allowed us to begin the design of a 2-lane bridge structure. We found that our future average daily traffic volume would be just shy of 13,000 vehicles per day. Using the Federal Highway Association's Roundabout Geometric Design Manual, based on the average daily traffic and desired entry speed for an arterial road, a single-lane roundabout would be most suitable. Using the design we conducted with Synchro 10 software, the schematic of the roundabouts were built using computer-aided drafting.
To start with the roundabout cost estimate, as previously stated, we were asked by our sponsors to do their alternative design, which consisted on a roundabout on both sides of the approaches. In order to achieve a loss level of service A and B while following MDOT and Federal Highway Administration standards, the toll road construction came out to be approximately 10,000 square yards, with an estimated of 9 acres that will be in need of slope restoration. A rough estimation of the dual roundabout was performed to complement the schematic design. Here we can see all the item descriptions that are needed in order to construct both roundabouts. The unit prices were taken from an average price breakdown from MDOT done in 2020. The upfront estimate cost came out to be about $750,000, in which the most significant cost was obviously HMA, which came out to be $230,000. This is approximately 1/3 of our whole budget for the whole roundabout.
Following MDOT standards for traffic control, temporary detour routes were constructed using proper signage and spacing. As we will discuss in the construction schedule later, we chose to do a full bridge road closure of 100th Street, as the detour routing to US 131 would have little impedance on the public, since there is entry to US 131 located just over a mile to the north on 84th Street. As shown in the figure, the detour routes of east and westbound 100th Street were routed to 84th Street as well. The detour was routed to 84th Street as it was the shortest possible alternative route to accommodate to the public.
Moving into our bridge superstructure, various parameters were established in order to begin with the structural analysis. The bridge spans over US 131 approximately 129 feet, consisting of 2 equal spans. With 12-foot lanes, 8-foot shoulders, and 1.5-foot barrier walls, the bridge cross-section was set at 43 feet. For bridges designed by the Michigan Department of Transportation, a unique loading labeled MDOT HL93 Modified is assigned in addition to superstructure self-weight. This modified HL93 accounts for the live and impact loads encountered due to heavy vehicles. The first alternative superstructure design we considered consists of prestressed concrete girders. Structural analysis was performed using LEAP Bridge concrete design software, where a model was built in accordance with MDOT specifications. From our research on similar bridge projects, an AASHTO Type 3 girder was selected as a trial member. The girder design was performed in accordance with the PCI Bridge Design Manual, which is governed by AASHTO LRFD design specifications. Bridge girders are specifically designed to resist flexure and shear over long span lengths. With this in mind, it is important to consider that pre-stressed bridge girders experience varying stresses throughout their lifespan. The first section analyzed is when the pre-stressed steel is initially released into the concrete, ensuring the girder is safe to transport and install. The second section analyzed is after the girders are placed in the superstructure, with bridge decking and haunches working with the girders to resist flexure and shear. This is often referred to as girders working in composite with decking. After understanding the girder section properties and the stresses due to loads on the bridge, we were able to estimate the required amount of pre-stressed steel in each girder as 21.6 strands. For a conservative design and idealized strand arrangement, we decided to try 28 pre-stressing strands. The steel is 1/2 inch diameter, 270 KSI high-strength steel. The first parameter checked within the design was flexural resistance. The table shown on this slide summarizes several stress checks required by LRFD design specifications at extreme fibers on the section. These include the top fiber of the bridge girder, where maximum compressive stresses would be expected, as well as the bottom fiber of the girder, where maximum tensile stresses would be expected. From the values within the table, it can be noted that the current design is adequate yet conservative. An iterative process may be used to decrease the number of pre-stressed strands and recheck the stresses. Another thing to consider in the design of pre-stressed concrete girders is the pre-stress losses. Over time, pre-stressed steel is subjected to stress losses and gains due to the deformation of bridge elements. These deformations include steel relaxation, concrete creep, and concrete shrinkage. Through design calculations, our team was able to check the total pre-stress losses against LRFD's allowable, and this section was adequate with a final loss percentage of 21.3% of the original stress. Next, shear resistance was considered. As expected, the shear resistance of concrete alone was not sufficient to resist the load specified. Therefore, we designed steel stirrups for the girder section. From our engineering calculations, we chose to use number 6 double leg stirrups at 12-inch on-center spacing for adequate shear resistance. The second alternative superstructure design we considered consists of steel girders. Structural analysis was performed using Leap Bridge steel design software using the cross-section shown on screen. From the maximum bending moments and shear forces seen within the structural analysis, a W33 by 141 section was selected as a trial member. Similarly to the pre-stressed concrete girder design, this design was also governed by AASHTO LRFD design specifications. When beginning our steel girder design, it was noted that MDOT recommends bridges with steel girders to act continuously over the entire bridge span to eliminate any expansion joints over center piers. This is important because the girders will not only need to resist maximum positive bending moments at a midspan, but they must also resist maximum negative moments over any piers. With this parameter considered, we also had to understand that the bridge girders will be working with the bridge decking to resist flexure once construction is complete. As referred to earlier, this type of combined flexural resistance is a section working in composite. This led us to the design procedure of checking maximum positive and bending or negative moments resistance along with shear resistance. From the diagrams on screen right now, you can see the maximum moments and shear forces provided by the Leap Bridge steel design software. When checking the flexural resistance strength at the 2 locations required, it is important to consider what bridge elements are helping resist flexure. This can be broken into 2 categories. The first being when the concrete deck is in compression at the maximum positive bending moment location, where concrete compressive strength can be considered. The second, however, is when the concrete deck is in tension at the maximum negative moment location, where only the tensile strength of the deck reinforcement may be considered due to concrete's weakness and tension. This occurs over piers. This category is shown on the figure on this slide. From our design calculations, you can see that the W33 by 141 girder is adequate in resisting maximum negative and positive bending moments. With the negative moment resistance only slightly above the maximum negative moment due to loading, the design is deemed economical. However, the positive moment resistance is much greater than the maximum positive moment due to the loading, which leaves room for improvement within the design. Further exploring built-up sections, such as thickened flanges at certain locations along the girder, may result in an even more economical design. For steel girders, Shear is rarely inadequate if flexural resistance is okay. The same goes for our design, where the shear strength of the girders are much greater than the expected shear forces.
The estimation process started with quantity takeoffs, which only involved the superstructure element of the bridge. Once quantities were established, MDOT unit pricing was retrieved by taking the average pricing from 2020 bidders. We also used MDOT Region Number 3 cost codes to enhance accuracy. A detailed estimate shows a cost comparison of the girders. Both girder options carried similar costs for the decking system, but total costs for pre-stressed concrete girders ended up about $70,000 cheaper than steel girders for the 100th Street Bridge. Aside from cost, a more in-depth weighted alternative matrix was developed. The matrix allows an effective analysis of the pros and cons for each girder design. The matrix carries increased weight for more considerable parameters. The pre-stressed concrete girders yielded a better total score as the final matrix was established. It's also important to note that the W33 by 141 steel girders in option number 2 have slightly easier constructability, as they are significantly lighter than the AASHTO Type 3 beams. Although both girder materials obtain some aspect of sustainability, steel girders utilize around 90% or more as recycled material. The parameters with increased importance, such as a lower lifespan cost and location, result in a better overall score for option number 1. Lower costs and the absence of splicing solidified the reasoning behind the selection of pre-stressed concrete girders. In addition to an in-depth schematic design and cost estimations, we assembled a construction schedule via Microsoft Project. This breakdown helps effectively convey a step-by-step construction process. Beginning in early March and ending in late August, the duration of the construction is projected at 234 days. A bulk of the schedule reveals the bridge construction as the critical path, whereas the roundabouts carry some flow. Of course, the full Gantt chart is available in our final report. To begin formulating a complex work sequence, a macro scale approach categorized major work items. Then, the work breakdown structure could be expounded upon, creating a more accurate construction schedule through our combined work experience and numerous consultations with MDOT personnel. Also embedded in the schedule includes proper construction sequencing, lane closures and traffic shifts, and key milestones. Although heavy equipment use is increased, accelerated demo during nighttime hours minimizes public impedance. The accelerated superstructure removals include the barriers, guardrails, the decking system, the girders, and the center pier. Alongside the early stages of the bridge construction, the east roundabout begins with the sequencing seen here. Near the midpoint, the west roundabout can begin to avoid any demobilization. The mirrored roundabout construction begins with the milling of existing surfaces and ends with paving only the base course of asphalt until a later date. The main considerations for constructing the new bridge revolved around preparation with formwork and steel rebar, as well as concrete placement, cure times, and tear down. The substructure starts with existing foundation demo, placing the new foundation, and then constructing the abutments and center pier. It is important to note that the detailed schedule depicts separate construction of the east abutment, the west abutment, and then the center pier. During the final stages of concrete placement, bolsters and a center pier cap are included. The early stages of the superstructure must follow proper lane closure methodology. The east girders are erected, then the west. Similarly, the false decking is constructed with proper lane closures. Then the complex installation of steel rebar can be set prior to the placement of the sleeper, approach, and deck slabs. Due to the large quantities, the schedule also includes a sequenced placement of the concrete. So towards the later stages of construction, we will street sweep the base course of asphalt before spraying a tack emulsion and paving the top course. Finally, permanent signage, site restoration, and any other punch list items can be completed.
To give a brief summary of what was developed by our team during this senior design, our main focus, as it says in point 1, was the effective comparison between the prestressed concrete and the steel girders. We then managed the assessment of the ramp intersection, which includes the dual roundabouts for the approaches. Afterwards, we came up with the cost estimates and construction schedule for the whole design. And finally, we showed some detailed drawing, which includes the roundabout, traffic and signage plan, and pre-stress and steel girders. Our senior design team would like to give major thanks to all the resources utilized throughout the whole project duration. We also want to acknowledge and give thanks to our sponsor MDOT and faculty advisors which guide us through the senior design. And finally, we are thankful for the school which allowed us to better prepare for the workforce in our respective engineer's career. Thank you all.
Excellent, great presentation. Now we're open for questions from our industry advisory board members.
Yes, Mary. I believe I saw Mary's hand.
I was just clapping.
Oh, it's just an applause. Thank you very much.
This is John Polasic. I was wondering about the approach road and the cross section. Did I miss the cross section for the roundabout as far as the asphalt paving and for that? Or did you do a pavement design for that?
Arturo, do you want to talk on that?
Yeah, we basically follow like past projects we have been involved, and basically we just like continue doing like the same schematic design, which involves like HMA. Well, first remove the old HMA we have and then just put it up the new HMA. That you can see if Tom, if you could go to the cost estimate.
To expand on that a little further, we took on the roundabout design to ensure we had an accurate bridge width when we designed our bridge. So we focused more on the schematic kind of sky view design, what it would look like for lane widths. So we really didn't get into detail of HMA layers or thicknesses. We went with typical from what we've experienced in talking with our sponsor MDOT for a cross section of what is expected on a roundabout, like if it's 3 layers, stuff like that. It's taken care of in our estimate.
Okay, what a wonderful job.
Thank you.
Thank you.
Thank you. Dr. O.
Yeah, I have 2 questions. The first question is, you propose a dual roundabout, but do you have any good justification that you propose? And second question is, have you considered any the pedestrian or bicycle path through the bridge?
Oh, should I?
So, go ahead.
Yeah. No, you can go ahead.
So basically our sponsor at MDOT asked us, or she recommended that we do a roundabout design, like a schematic design, as they had it as one of their proposals before they built the bridge. And so we kind of took off from there. And it was a little bit out of the scope of our project initially, and we really wanted to get going on the girder design or the bridge design. So we needed to add our proper geometrics for the bridge. And what was the second question again?
Yeah, so considering the pedestrian paths and bicycle route.
Yeah,
Bridge.
so the pedestrians, it's more of a rural area. We did consider it, but it was mainly out of the scope of our project.
After speaking with MDOT, it was 50-50 when it came to considering for a new bridge construction pedestrian in the area. There's not a lot of seen pedestrian traffic. They took note of it in their traffic studies, and it was noted that there wasn't a lot of pedestrian traffic. So it's something that we didn't consider specifically for this project. However, we did consider in our schematic roundabout design and estimate signage and striping for pedestrians to cross the roundabout safely.
Okay.
Is there any other questions? I can't see any hands.
I have a couple questions. First one, you predicted 50-year traffic, and we designed bridges for 75 years. So now actually we are looking at designing bridges for 100+ years. So what is the reason for that? And then the second question, how you use the software to analyze and design the bridge? So how did you verify your analysis results from fundamental approaches? And then the third one is a comment, because you use FHWA example to do a design for MDOT. FHWA examples are old and they are not following MDOT policies. So we have actually done workshops for MDOT designing pre-stressed girder bridges and steel girder bridges. So I don't know why you didn't acquire detailed design examples from MDOT that we have provided to their design engineers to design these bridges that well explain the analysis and design procedures according to MDOT policies.
To answer your first question, I believe talking about using the structural design software, is that?
No, first one is the service life, because you're looking at 50 years. Now we designed for 75, actually now we're going for 100+ years. So why you use 50-year predicted traffic?
We communicated with our sponsor on that and checked that a 50-year bridge design life was adequate for our analysis, and they were okay with that at MDOT. That's new information to me, the 75-year, but it's definitely something we can consider for the roundabout when we look at the traffic volumes if we were to further dive into this project.
Hey, Dirk, I think it's also important to note that with your girder layout, the reason that we've selected the current layout is so there is that expandability down the road if needed. So if that bridge needs to be expanded or worked on, Dirk, correct me if I'm wrong, but you had your girder layout for that reason.
Yep. To answer your second question, Dr. Uppel, the superstructure analysis was performed using the software. This was a type of way for us to include and learn a type of software on the project. Basically adding loads and like watching tutorials to fully understand the structural analysis aspect of the software, we thought was a very cool and accurate tool in combination with the HL93 modified loading, because it's a complex loading system. There is a way to do it by hand, and we did consider that, but we left time for ourselves to do the design work by hand. So we did not perform the design work using those softwares. We strictly used it for structural analysis. And then to answer your third question about using the Federal Highway Administration's example for the steel girder design, it was a type of general example for us to follow in combination with our school, like what we've learned in school, and we deemed it adequate for designing a general superstructure approach. We could have worked more closely with MDOT to receive more. We didn't hear anything about that from who we talked to at MDOT, what you referred to, but it's definitely something we could look into if we were to further expand on our design for steel.
So
Thank you for the
just
question.
since we have a lot of students listening, so first thing you need to look at, I mean, who is even teaching bridge design at Western? Okay, and we have done all the training for MDOT engineers, and you are not utilizing the resources available, and you are going, so you are not learning the procedures that you're supposed to learn. That's one thing. Second thing is using a software as a black box is not acceptable when you have fundamentals. So you don't demonstrate how you are supposed to use your fundamentals to verify the outcome of the software because it's a black box. You put something wrong in and you get something wrong out. So that's something, I mean, always we see students telling that we use the software, but these are simple structures that you can analyze by hand and verify. And unfortunately, we don't see that. That's a big drawback because now you see that why you need to learn structures because you don't use it. So it's a general comment, not for you, but for everyone. So that's unfortunate because you don't see the value of learning fundamentals.
I've got 9:30, so